Now it gives me great pleasure to introduce Professor Satoshi MAEDA. Professor Varnik already introduced Professor MAEDA in the beginning of the symposium, outlining what the institute that he directs, ICRAD, at the Hokkaido University has been doing really in a very interesting way. I witnessed this in the last few years. But briefly, Satoshi received his PhD from the Hokkaido University in 2007, and then under the supervision of Professor Koichi Ona, and then he was a postdoc working with Professors Ona and Keiji Murakuma. And since 2010, he's been holding academic positions. So currently, he is a professor at the University of Hokkaido and director of ICRAD, received numerous awards, and we're looking forward to hearing about quantum chemical potential energy calculations. Thank you.
Thank you very much for the kind introduction. I'm Satoshi MAEDA from Hokkaido University. And it is my great pleasure to be a part of these wonderful meetings. I'm kind of new to this society. And Professor Varnik kindly gave me an opportunity to attend this meeting. So I'd like to thank very much for your invitation. So the reason why he gave me the opportunity is we recently collaborate closely to each other in our new institute called WPI ICRAD in Hokkaido University. Let me start with some introduction about the Hokkaido University and the WPI ICRAD. The Hokkaido is a North Island in Japan, and Hokkaido University is situated in the Sapporo city, which is the biggest city in Hokkaido Island. And as you see, this is our building, and as you see, there are lots of tall buildings behind it. So our university is situated in the city center, and in the city center of Sapporo is very well developed, and you can find good hotels, restaurants, drinking place, whatever. And outside the city, there is a big nature, and you can find trekking places, onsen places, skiing places, etc. Even inside the campus, you can see very beautiful sceneries depending on seasons. And now in summer, campus looks like this. So I'm in charge to hold the 10th French-Japan workshop on computational methods in chemistry in Sapporo in July next year. So together with Professor Varnik and Professor Funatsu. It is my great honor to hold this very nice workshop, and I hope that I can invite some of you to this workshop in the next year. Okay, so what is ICRAD? So ICRAD is an institute which was established in 2018, and since then I was a director of. Has been a director of this institute. So its mission is to revolutionize chemical reaction design and discovery by integrating computational chemistry in chemoinformatics and experimental validation. This is the picture of all the members. Now we have 90 researchers, and almost half of them has foreign nationals. And on this slide, computational chemists are marked with blue, and experimental people marked with green, and informatics people marked with orange. And we now have 15 laboratories led by senior PIs, and among them, 3 laboratories are organized by foreign PIs. For example, Professor Varnik organized his satellite laboratory and participate in our collaborative researches among these laboratories. And Professor Benjamin List, who is a Nobel Prize winner 2021, he also has his laboratory, and also Professor Mikhail Rubinstein of Duke University has he's a physics-based macroscopic simulation researcher. He also organized his satellite laboratory. Also, we have 4 additional laboratories organized by young peers. And these young people's contribution is very much important, especially in the future development of our institute. We recently got our own building, which is a 4 stories building and includes a 5,500 square meter lab space. And the specialty is a so-called super mix lab. It's situated in the 2nd floor, and this is a picture, and researchers from all the 3 disciplines works together in this super mix lab and exchange ideas to generate new collaborations. Okay, so let me introduce a few projects running in our institute in very, very brief. So this is a collaborative project among 2 laboratories, and this is a project to discover the design and discover the chemical reaction from scratch based on DFT and quantum chemical calculations. So we actually achieved the discovery of new synthetic methods with this direction. And this is also the collaborative study among 3 laboratories. Professor Barneck's group is included, and this is a catalyst design project. And in this case, they tried to discover the beta catalyst of the Professor this IDPI organocatalyst. And they modeled this catalyst with Professor Barneck's chemoinformatics techniques. And we also acquired lots of experimental data using the robotic synthesizer and did some machine learning. And finally, we discovered a new catalyst. And we also have, so this is also the collaboration among this, in this case, 5 groups are involved. And this is the design project of hydrogel, functional hydrogel material. So in this case, we utilize a macroscopic simulation, quantum chemical calculation, and machine learning to discover, to design many functional hydrogels. We also, there is one laboratory led by medical doctor, Professor Tanaka, and in this project, they tried to make a strategy of the cancer diagnosis strategy to quickly discover the cancer stem cells using their hydrogel activated reprogramming phenomenon technique and drug in silico and experimental based drug discovery. So that very brief introduction of our institute. So if any of you have interest, please feel free to ask me even after this conference. Please send me the email. Okay, so let me move to my own research part. It is a ab initio reactivity exploration and prediction. So what we do is very simple, just to explore the quantum chemistry-based potential energy surface to sample the lots of stationary points, including local minimum structure and transition state structures. So basically, if we sample or we obtain all the stationary point, then very accurate prediction of chemical reaction can be achieved. However, it is a very difficult task because of the very big volume of the potential energy surface. We have 3n-6 vibrational freedoms, and essentially it's a kind of very difficult problem to get all the stationary point. But there are lots of development, especially in recent years, with the aid of the development of advancement of the hardware and softwares. So I recently wrote a perspective article together with Professor Schwegel, who is a most important person in this field. And so this is a kind of omnibus type article, including lots of topics, and we wrote the part of potential energy surface. And this is the part of potential energy surface is only 3-4 pages. So this article can be starting point to run this field if you are interested in. Although there are lots of methods to sample lots of potential stationary points, it is not enough that just sampling a sum of stationary points automatically. So let me to predict unknown chemical reaction. So with this slide, let me explain how much difficult to predict unknown chemical reaction is. So this is a simple textbook reaction. So this is just an example, so no meaning in this slide. And so this is its mechanism representation, and this reaction consists of 8 elementary steps. So also you don't need to understand these elementary steps. So this is a so-called reaction path network representation. So each node corresponds to each local minimum of the potential energy surface. And these 8 elementary steps are highlighted with these white arrows. So in an ordinary mechanistic study, just obtaining these 8 elementary steps is okay. However, to predict unknown chemical reaction, it is not enough at all. So in a prediction of unknown chemical reaction, one needs to prove that no other channels open except for these 8 elementary steps. To prove that, one needs to get like this very complex chemical reaction path network. So it was a very difficult problem to get this reaction path network systematically, but recently we achieved systematic method to generate this kind of reaction path network. So our basis is a reaction path calculation method, so-called artificial force-induced reaction, AFIR method. So its algorithm is pretty simple, just pushing fragments together or pull them apart. So this is its simple illustration as for the reaction between atom A and atom B. And on this potential energy curve, there is a barrier here, and the ordinary simulation will be trapped behind the barrier, and that takes a long time. So we put a force term, and it's a linear function of the distance RAB and the constant parameter alpha. So this force on this force modified potential, just by minimizing this function, one can very easily get the product, and afterward one can identify the position of transition state also. So this is the actual form of the force modified potential energy surface, and I don't go into details of this function, but there is a double summation for fragment A and fragment B. And please look at these examples, and starting from this configuration and setting fragment A here and B here and minimizing this function, and then one can predict this reaction. And starting from the same geometry, setting the fragment A here and B here and minimizing the function, one can predict another reaction. So this way, we can generate many different reactions in using based on DFT calculations. So using this technique, we can construct a so-called reaction path network. So we first start from the reactant point and set a fragment A here, B here, and then get the reaction path by minimizing the function. And so please think that this point corresponds to the initial structure, and this line corresponds to this reaction path, and this point corresponds to the product. And by setting A here and B here and doing the same thing, one can get a different reaction to the different product. And by doing this systematically, starting from the initial structure, one can get lots of reaction pathways to other products. And this is repeated again and again, starting from all the obtained structures. And finally, one can obtain like this reaction path network. So this is an example of reaction path network for a system consists of 4 carbon atoms and 6 hydrogen atoms. Does this work? So I'm not familiar with this one. So okay. Yeah. Okay. And yeah, so this calculation was started from the, uh, mm, so this page is very heavy, so mouse pointer doesn't work well. So this calculation was started from the middle of structure. It's a one-strip diane, and our algorithm automatically generated like this very complex reaction path network consists of 65 local minima and 800 transition state. So obtaining like this comprehensive reaction path network is difficult work, but now we can do this with our AFIA method. But on this network, most of the parts are useless because they have very high barriers, high energies. So we introduced a kind of truncation technology based on chemical kinetics. So this page shows the kinetic simulation. This is just a textbook thing. And once one gets like this energy profile, then one can calculate a rate constant using the delta delta G free energy difference values using this rate constant equation. And then one can formulate like this rate equation. And basically, by solving this equation, one can simulate the chemical reaction. However, this rate constant matrix consists of lots of elements with very different order of magnitude. For example, the conformational rearrangement rate constant is very large, like 10 to power 13th, and chemical bond rearrangements rate constant can be very small, like 10 to minus fifths parsec, etc. So this equation is very stiff equation, and ordinary numerical approach doesn't work. So we developed our own kinetic simulation method, so-called rate constant matrix contraction, RCMC method. The idea of this method is combining kinetics with so-called fuzzy clustering in graph theory. So we focus on the shortest life state, and this state is contracted to adjacent state with some ratio. And we eliminate this shortest life state and reconstruct the reaction path network. So by repeating this contraction again and again until all states with life shorter than user-defined Tmax, as the contraction is applied to all states with life shorter than Tmax. So this Tmax usually set as the reaction time of actual chemical reaction. For example, if you treat a reaction which takes 1 hour after mixing, and then this Tmax is set as 1 hour. And after this series of contractions, finally, a coarse-grained network is obtained consisting of a few so-called super states that interconvert on a time scale longer than Tmax. And there is a very important feature in these methods. So each super state is expressed as a linear combination of original local minima and a contribution ratio of the reactant local minimum to the product super state corresponds to the reaction yield at T called Tmax. So just applying this method to the obtained reaction path network, we can predict the reaction yield very efficiently. So we combine this method with our AFIA reaction path exploration. So first, our exploration starts from the initial structure, and then AFIA get a local reaction path network. Then we apply our RCMC kinetic simulation so that we distinguish the region which is accessible from the reactant local minimum within a given experimental condition or not. So the exploration is continued only from the kinetically accessible local minima, and a larger network is obtained. And then we apply the RCMC method again to identify the kinetically accessible area and boundary between kinetically accessible and inaccessible area. So finally, we can get a reaction path network, which includes the kinetically accessible area and the boundary between kinetically accessible and inaccessible area. So this network tells that these parts are kinetically accessible and other channels are closed because we identify the boundary between kinetically accessible and inaccessible area. So the reaction path network obtained in this way can be an actual prediction of unknown chemical reaction. So we call this forward on-the-fly kinetic simulation. So the input is a reactant species and some experimental conditions and some DFT parameters. So after starting the calculation, our code produce like this reaction path network, which includes kinetically accessible area and the boundary between accessible and inaccessible areas. And output is a major product, a byproduct, and their reaction yield. So let me show one demonstration. This is a demonstration for so-called Strecker reaction. These are the reactant species, and in one simulation, we can consider 3 different temperatures, and a reaction time was set to 1 day. And this is DFT parameters. So this simulation provided like this very complex reaction path network, including about 8,000 local minima and 20,000 reaction elementary steps. The reason why our network so complex is we also consider the pathways of conformational rearrangement. Usually people think that a conformational rearrangement is a very quick process and it's not important, but it's not true because some chemical reaction can happen only from specific conformation. And considering the conformation rearrangement pathways also, we can also include the conformational entropy during the chemical reaction. So this reaction path network representation can precisely describe the chemical reaction. So we have a graph user interface, so-called general map, and it first visualizes all the species predicted on the reaction path network, and there are some options to narrow down the species, and these two. So this button, once we push this button, then species that get a high yield remains. So at a low temperature, this cyanohydrin was predicted to be the major product, and higher temperatures, this aminonitrile was predicted as a major product. So this is consistent with experimental results, and we can visualize the elementary steps between the starting structure and that aminonitrile product structure. And this mechanism is also consistent with the known Strecker reaction. So I can say that in this demonstration, our calculation predicted the Strecker reaction, its product by product, their yields, and the reaction mechanism from scratch without using any previous knowledge or data. Okay, so the reason why we call that forward simulation is because we also have backward simulation. So it is also called quantum chemistry aided retrosynthetic analysis, QCALA. So the idea is very simple, just starting from the target product structure, and we search the reaction pathways in the backward direction towards the reactant candidate. So idea is very simple, but realizing this calculation was a very difficult task because in this simulation, the combinatorial explosion of the possible reactant species easily occurs. So kinetics-based confinement truncation is also necessary for this simulation. However, the kinetic simulation is formulated only for the forward simulation. So it usually starts from the initial structure and the simulation goes to the product structure. So we needed to invent a so-called inverse kinetic analysis. So I do not explain details of this inverse analysis, but I explain just an idea of this simulation. So this slide shows the procedure of our RCMC method. So RCMC, as I mentioned, the RCMC method make a kind of fuzzy clustering of local minima. And for a given reaction profile, it apply the so-called contraction procedure to distribute this local minima to adjacent local minima. And this contraction is repeated again and again so that all the superstates had a long lifetime. And finally, we get a coarse-grained reaction profile like this. And in my, as I mentioned in the explanation about RCMS method, there is a very important feature that the contribution ratio of each local minimum to the product superstate directly corresponds to the reaction yield in this formalism. So just applying RCMC method just one time, then we can estimate the reaction yield of reactions starting from all the predicted reactant candidates. So this is very efficient. So yeah, this made the inverse kinetic simulation possible. So I will show one example. It's application to this Pasolini reaction product. So we started from this structure. We got like the reaction path network. So these two networks are basically the same networks, but left-hand one is colored with stability energy of the predicted species. And the right-hand one is colored with the yield of this desired product through reaction starting from each point. So starting from red point, this desired product is obtained almost 100 yield. So among these red nodes, this node corresponds to this species, and this does corresponds to the reactant of Pasolini reaction. So in this case, just providing the product of Pasolini reaction, we were able to predict the Pasolini reaction. And you see many other red nodes. So these can be alternative candidates of possible reactants to give this product. So this page shows some of them, and yeah, so most of them are chemically very reasonable, and also yeah, so this list shows some high energy species like this, and this predict that these species can also be a possible reactant to get the product. So this backward simulation predicts hundreds or thousands of chemical reactions in single simulation with their reaction yield. So this is an application to a simple natural product, and so this is a known retrosynthetic pathway of synthesizing this one, and yeah, so this route was successfully rediscovered. So by this method also. So by using this forward and backward simulations, we have collaborated with our experimental team, and we first calculate the reaction path network in a forward way or backward way, and then obtained predicted reaction pathways are verified by experimental groups. So this way, we were able to discover some new synthetic method. So we recently published review article, and if you are interested please read it. So we recently collaborate heavily with informaticians. So this is a collaboration with Professor Tsuda of University of Tokyo. And so our AFIA method tries many tasks to calculate many different reaction pathways. And some tasks are successful and some tasks are not successful. So we trained a graph neural network to run the successful and unsuccessful tasks, and using this graph neural network, the computational cost was reduced very much. And we also tried transfer learning, applying this method to different systems, and it also worked very well. So we recently utilized a so-called machine learning potential. So this technology was introduced by Professor Banek's group, especially Dr. Ruben Stahl worked hard on this combination between machine learning potential and our real kinetic simulation technology. So we start with a semi-empirical simulation, and then we get lots of local minima and transition state. But at the semi-empirical level, the result is not accurate. So we recalculate this local minima and transition state at the DF2 level and train the potential. And this exploration, sampling, training is repeated again and again until the kinetics converges. So this way it can be so the predicted reactions in this way can be as accurate as DFT-based exploration. So with this technique, 10 to 1,000 times speed acceleration was achieved. And recently, we can apply this method to very big system, like shown here. And this is a catalyst developed in the Professor List group, and this very big catalyst control the selectivity of the product. And now we can do the reaction path network calculation for like this very big system. We also are applying this technology to many different programs, and now I'm confident that our reaction prediction technology can be applied to a variety of chemistry. Previously, I didn't very much confident, but with this machine learning technique, now I believe that this technique will be very useful. So also we tried some so-called generic neural network potential provided by a company called Preferred Computational Chemistry. So I saw that it's not so reliable because it is trained with many other systems, but their database is so big, using very big resources. And to my experience, it was at least reliable, at least to get a qualitative prediction. And in this case, we consider this very big slab system, and including the 900 atoms, and simulated the complete oxidation of methane molecule. And we got a reaction path network, including more than 20,000 local minima. And this network successfully explained its mechanism. And the result was very consistent with previous DFT-based calculations. So yeah, this kind of company produced potential can also be very useful. So now we are utilizing that backward simulation approach. We are now constructing the chemical reaction database fully based on the quantum chemistry. So as I mentioned in the explanation, with a single application, single network calculation, we can get thousands of chemical reactions with their yield data. And this computation quantum chemistry-based database has some advantages against the experimental-based database because this database includes species that is not readily available in experimentally. And also this database includes zero or near zero yield of chemical reactions. So yeah, so this database almost unbiasedly searches for many kind of reactions and maybe can be a complement to experiment-based reaction database, I believe. Okay, so I think I have 10 minutes. So, for 5 minutes.
You've got 3 minutes.
Oh, so I will explain our new concept, which is a continuous reactivity optimization utilizing the so-called yield derivative. So this is a very new concept, and I have explained this only 2 or 3 times, so I'm afraid that I can explain very well, but yeah, I try to explain. So yeah, as I mentioned, so now RCMC can analyze the complex reaction path network very efficiently, and it provides very efficiently the predicted reaction yield. So our mathematical colleague, Dr. Oki, formulated the mathematical representation of this RCMC method. So he formulated the mathematical representation of reaction yield based on this network data. And he said that he can also derive the derivative of this yield in terms of stationary point energy. So yeah, so this I was very much surprised because we can represent a chemical reaction in a mathematical way, and this reaction yield is now can be derivative is available. And by calculating this derivative, we can identify the important stationary point in this reaction path network, and we can identify this transition state is most important. This local minimum is next important, etc. And in parallel, our colleague, a young colleague, Dr. Matsuoka, has been working on to model the ligand for organometallic catalysis with mathematical form. So this is some examples. And he also derived the energy derivative of in terms of this molecular structure parameters. So now we have energy derivative of molecular structure, and we also have yield derivative in terms of energy. This means that we now have the yield derivative in terms of molecular structure. So now we can make a continuous optimization of reactivity in a given system. So now we are working on the design of CO2 utilization organometallic catalysis design with this technique, and the initial results is now in preparation. So this technique costs at the moment very much because we need to calculate reaction path network, but with the advancement of the computational technology, this very blind optimization of reactivity, continuous of reactivity, fully based on quantum chemistry, will be, I believe it will be a routine in some years. Okay, so this is a summary. So we have developed a FAIR method, and we combined it with kinetics method called RCMC, and we made many applications, and now we are working on its application to many big systems, and also we are working on the fully ab initio-based chemical reaction database, and also now working on the quantum chemical reactivity optimization concept. I'd like to thank my colleagues, theoretical and informatics colleagues and experimental colleagues, and I'd like to thank the group members and some financial support, and the environment provided by WPI was very important to achieve this research. And also I'd like to thank some computational resources. So this is just another advertisement. Our GRM23 code is available from the company, and you can access through this link. And we also provide a collaborative system to teach how to use this software in Nightbread, and if you are interested in, please also access to here. So that's all. Thank you very much.
Thank you, Dr. Maeda. So we're out of time. Quick question, and then move the discussion upstairs.
Thank you very much. Amazing work.
Oh, thank you.
This was a very nice to see that you apply GNN on your reaction graph.
Mm-hmm.
However, it reminds me that it's kind of knowledge graph. So my question is, have you thought about applying some graph learning techniques to learn not just a couple of points separately, but the graph entirely?
I haven't think about that. Maybe, yeah, we collaborated with Professor Barneck's group, and we applied GTM, graph topograph mapping technique to the network. But yeah, so many kind of analysis can be applicable, I think. Yeah, so if you have some nice idea, it's very much welcome.
Okay, so with that, let's finish the morning session. Thank you.
Thank you.